Okay, like I said at the beginning, a lot of the algebra topics that we do tie into things you already know. As we pull out things that you've learned before, I'm going to mention it so that you can make the connection. Okay, some of the things you see are not going to be brand new. Okay, you might see it in a different way, but a lot of these skills you already know how to do. So here's our example. You set aside part of a rectangular plot of land for a garden, right here, and you're going to seed the rest with grass. Okay? Grass seed costs 3 cents per square foot. First, we're going to write an expression for the total cost of the seed, and then we're going to calculate how much money would be. Or if we bought $50 worth of seed, how much we would have bought. How can I represent, using an expression, the area of the grass? What shape is that? It's a rectangle. And how do I find the area of a rectangle? I need the length and the width. Okay, so I need the length and the width. What's the length of that grassy area? 45. Okay, so you could say this is the length. What's the width? Say it again. Why is it x minus 10?
Because you only want to do the grass part, and that other 10 is for the garden.
Right, so take a look at this image. If this whole thing is x, that doesn't just represent the width of the grassy area. I need to take away this chunk. And based on this and the properties of rectangles, if this is 10, then this needs to be 10 as well. So I can represent this as x minus 10. How could we find the cost? What would you do? Like if you knew you had to multiply length times width, what would you do with that expression? The 45 parentheses x minus 10. Distribute, absolutely. Okay. If you distribute that, something that you've done before, but you would be distributing a monomial, one term, the number 45, to a polynomial, x minus 10. Okay. Now, if I distributed that, then I could find the cost, that 3 cents, and I could set it equal to 50. So what would I do here? You just told me I would distribute, so I'm going to jump a little bit ahead for you and do that. But I still need to multiply this by 3 cents. And how would I, what am I going to do there? I can distribute again. I could do 3 cents here, and I think it's 1.35 and minus 13.5. I think it's something like that. Equals 50. Okay, we kept going in the other class. Yes, there is an x right there. So I can solve for x. And I'll try to move a little bit because we lost a little bit of time. 1.35x equals 63.5. And I can solve for x here. Okay. The solution of this problem is not our focus right now. What we are trying to see is how we can actually multiply a monomial by a polynomial in a real world situation. Okay, I think it was 43 point something. Not necessarily important right now. We can use the distributive property. So you have already done the distributive property. This should not be new to you. Right? You know the idea that if you have that number outside the parentheses that represents this much of everything inside. We can use the distributive property to multiply a monomial by a polynomial. The distributive property would stand here, even though the number outside, or I should say the term outside, is a 2x. I can still multiply that through. There are 2 ways we could do this. One way is just showing the algebra. I'm an arrow girl, so I like to show that I'm multiplying everything here. If I distribute, I'm really multiplying 2x times 3x, and then 2x times 1. If I do that multiplication, 2x times 3x, I really have 2 times x times 3 times x, which is 6x squared. And 2x times 1 is represented by 2x. So you could do that using just the calculations that you've done before. Another way you could do this is with visual. If you need an area model, you could set it up like this. The length here of this rectangle is represented by the 3x plus 1. And the width here is represented by 2x. If I break it out this way, you can actually see where the numbers are coming from. You can see that if I find the area of this square, x by x, it would be an x squared, an x squared, an x squared. 3 more x squareds, and then you have your 2 x's. The visual comes in handy when we start to multiply a binomial times a binomial. Okay, 2 terms times 2 terms, which we will do next week. We already did that. How can I simplify this? So take a look. We're stepping it up a little bit. What should we keep in mind? There's 2 things. 2 things we want to look at. We have the same type of problem. We have a monomial outside the parentheses, and we want to simplify. What kind of polynomial do I have inside the parentheses there? It is a trinomial. How do you know it's a trinomial? It has 3 terms. Good. What should I keep in mind when I multiply? Where could mistakes come up? There's a few things that are pretty common when it comes to mistakes. Think about if you were to multiply and distribute that negative x to the third. Where might you make a mistake?
If you distribute to the 9x to the 4th and 7.
What do you mean?
You can only distribute it to the 2x to the 3rd.
Why?
Because it's the same exponent.
What operation am I doing if I distribute? Multiplying. Are there restrictions on what I'm allowed to multiply?
Only restrictions on what you're allowed to combine.
Right, there's restrictions on what I can add together, but right now, if we're only multiplying, could I multiply that negative x third by everything inside? Yes, I could. I absolutely could. Just like before in previous units, I can multiply the 2 by an x and a 5, right? I really have 2x plus 10. Same thing, it doesn't really matter that we have exponents now. I can still multiply. When we talk about the distributive property, regardless of if there's exponents or not, where do a lot of people make problems when we distribute?
That's how I distribute to everything.
Signs and not distributing to everything, absolutely. So if you're going to distribute here, you are multiplying that negative x to the third times everything. So what are we really doing? Negative x to the third times 9x to the fourth plus a negative x to the third times negative 2x to the third plus a negative x to the third times a 7. You don't have to break it out. You could just show the multiplication. Taking it to the next level, I'm now multiplying x to the third, negative x to the third times 9x to the fourth. What do I need to consider when I'm multiplying those terms? There's a negative, so what would my coefficient be here if I multiplied? Just 9?
Negative.
A negative 9. Why is it a negative 9? Yeah, this is really a negative 1, and a negative 1 times 9 is negative 9. What's my exponent? Why is it 7? The exponent here is 7 because, like our last unit taught us, if we multiply with the same base, we add our exponents together. This really is negative 1, x, 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 9, x, 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 and x. So really, what are we multiplying? 9 times negative 1 here. And then we have 7 x's, x to the 7. That would be another big mistake that people make, is not realizing that when you multiply, you can still add those exponents together if their bases are the same. So we have negative 9x to the 7th. What would our second term be?
Positive 2x
To the 6.
Good, that's a 3, I'm sorry. Good, positive 2x to the 6th. Negative 1 times negative 2, x to the third times x to the third. What would our last expression be? Or our last term, I should say. So when we multiply a monomial times a polynomial, what are we really doing? It is a combination of 2 things. 1, the distributive property, something you have done before. 2, multiplying exponents, right? We have the same base. What can we do with the exponent? If we have a different base, that's not necessarily a rule. If I multiply 2x times 3y, I have 6xy. You'll see examples of that as we move forward. And I hope when you see this, you think, I can do that. I know how to distribute. I might make little mistakes, but I know how to distribute. Might make some mistakes with the exponents, but for the most part, I know if I have the same base, I can add my exponents together. If you still need to break it out this way, you can do that, right? You do not have to rush through any of this.
For negative 7x to the third,
Yep.
why is it not negative 7x to the fourth? Because sometimes I get confused when I put like a 1 on top of the 7.
Okay, if you're going to add the exponents, the base would need to be the same. Is there an x here? No. If that was 7x, it would be x to the fourth. It would be 7x to the fourth. But if it's not an x, it's just a constant. So imagine you're saying that you have 7x to the thirds. So you have 7x to the thirds. Oh, right, I already broke it out, so I'm going to skip over. Are any of the monomials in this expression, are any of the terms like terms?
No,
Why not?
because they don't have the same exponent.
They have the same variable, but they don't have the same exponent. I cannot add together x to the 7th with an x to the 6th with an x to the 3rd. That would stay. This is done. That's all I would do. I'm done. I've simplified. I've multiplied it out. If I could add it together, I would, but I can't. No like terms. So at this point, you would be done. You multiplied your monomial times your polynomial. You're good. I want you to try these two. Like 3 minutes. 3.5. So 3.5. Distribute the term on the outside. Whether you use arrows or you actually break it out, it's your preference, whatever works for you. You don't have to do this in silence. A lot of the practice is what makes this a little bit easier.
That'd be just bring that. I think oh yeah. Makes sense. I get that. It's literally, it's small. It's still
So like how you broke it up.
Dolce Martinez, Panay Keys, and Carla Mel Lopez to the main office immediately.
Anytime 7
Do we need more time on the first one? Or do you want, can we start to go over? I see some of you have done all of both.
Yeah, I want to see.
Okay, let's take a look at the first expression. Just like we learned when we distributed 6, or 7. So we practice a lot of distribution here. You can distribute any term outside by everything inside. Next week, we're going to start to multiply a binomial times a binomial. So it won't be just one term outside, it'll be 2. It's fun. I actually love these topics, they're my favorite. Okay, if I multiply 4t times t squared, what's my coefficient? 4. Yep. What's my variable? T. What's my exponent? Why is it a 3? Okay, if this is a 1, right, there's just one t there, and there's 2 inside. What I'm really multiplying, that term is 4 times t, and then in here, it's t times t. So that would be 4t to the 3rd.
Hello.
Can I put my phone on charge?
Yeah. How about the next term? 4t times negative 6t. Coefficient is what? Negative 24. Variable is a t. Exponent? 2.
Yes.
There's a t here, and then this would be like a t to the first. And then the last term. 4t times 2. 18.
Yes.
Can I add anything together? No. I can't combine a t to the 3rd with a t squared with a t. So I'm done. Alright, we can go over the next one, maybe a little bit quicker. What if I distribute that 8a squared to negative a to the 7? Who wants to tell me what that term would be? David, go.
Negative a to the power of 9.
Perfect. Negative 8 because you're multiplying 8 times a negative 1. A to the 2nd times a to the 7th, a to the 9th. Who wants to give the second term 8a squared times 7a? Jen.
Plus 46a.
What's the coefficient?
46.
Check your number.
56.
56, yep. 56. And what was your exponent? I'm sorry.
A to the 3rd.
To the 3rd. Perfect. Who wants to give the last one? 8a squared times negative 7. Zara.
56a squared.
What's the sign?
Minus.
Good. 56a squared. Perfect. So, if you're thinking about multiplying something out, and you'll see the extension next week when we multiply binomials, still the same thing. You're distributing, right? The only extension, you added a little bit of what we did last unit, where when we multiply with the same base, we can add our exponents together. So we can do the opposite. Imagine we had that term on the outside and we multiplied it through. We could do the opposite of that. Instead of multiplying a term through, we can actually pull a term out, right? Almost like division, it's factoring. We can factor out a monomial just like we distributed it through. So we're reversing the process here. Now, when we factor out, we need to find the greatest common factor. Okay, it's been a little while since you've done that, so we're going to go over a strategy today to do that. I'm going to show you at the end, after I stop the video, part of tomorrow's lesson, since I'm going to miss the first half class. Okay.
Once again, Kanaya Keys and Carla Vale Lopez.
I'm going to take the greatest common factor out of every term. I'm looking for what do they share. Like, what did I have that I multiplied through that resulted in that? And the only way I'm going to be able to do that, you might be able to see it already. And as you do these more and more, you will. But we can actually break it out. How can I break out 5x to the 3rd? What am I really multiplying?
5 times x times x times x.
Good. So that's really, those are the factors of 5x to the 3rd. How about 25x squared?
25 times x times x.
Can I break anything down further? Yeah, 25 is actually 5 times 5.
Oh,
Good. How about 45x?
9 times 5.
So you could do 9 times 5 times x. Can I break anything down further? Yeah, you could rewrite 9 like that. How can I physically identify what the greatest common factor is? Look at the entire breakout. Who can tell me what is the greatest common factor between all 3 of those terms? Don't call it out. Kate. You were mid-yawn. I didn't hear it all. What was it? Is that the greatest common factor? That is a common factor. Is there more? Okay. You two combined, got it. They share a 5,
But they also share an
and they share an x. Do they share anything else? No. So what would their greatest common factor be?
6.
5x. I could factor it out. Now in a few minutes I'm going to show you what we could do. Okay, so let's say we factored out the 5x. What do you think would go in the parentheses? If I needed to fully factor the expression, how would I figure out what goes inside the parentheses? Remember, I'm doing it in reverse. I need to figure out what was inside here, that when I multiplied the 5x, I ended up with 5x cubed plus 25x squared plus 45x. How do you think I'd find what goes inside? If I know the greatest, if I identified my greatest common factor, how can I find what's inside? Can you say it louder? Everything else. Yeah. So what's left from this term? X squared. What's left here? 5x. And what's left here? 9. Oh, just 9. That's how we can find it. That's actually the focus of tomorrow's lesson, which I'm going to give you a little sneak peek. We're probably just going to do. But today we're only working on that. Finding the greatest common factor. Again, you've done greatest common factor before. This is not new. That skill is not new. You're seeing it in a different way because it's at an algebraic level. But that's something you learned in like 5th grade, 4th? When did you do greatest common factor? 6th?
Yeah.
Okay.
No.
So it is still late elementary, early middle. Okay. We're gonna skip. I'm gonna pause this video first.
Laura.